as you know, up to now we have covered the beam designs, column designs, slab designs, and also the footing designs. So this document gives you the overlook for all kind of design procedures, the equations, and the way of doing it. So I will avoid many of the things that we now need to consider the calculation today's lecture, because we had discussed in our lectures. So these are the normal deflection, these criteria we do discuss, and the table, all these things have been discussed. So let me go for the examples and work on it. So this is one of the examples that a simply supported beam have an effective span of the 9 meter and support loads are shown. The determines to suitable dimension for the effective depth. So some of the students ask, how do you recognize, how do you apply the thumb rules for designing the slabs and the beams for the initial sizing? We call it is a preliminary initial sizing. That means once you decided the full structure, you just put the geometric sizes of the structure, then you will be able to take it off while doing the design. So if there is any mismatching, for example, the required sections that for the particular, let's say the beam or the column, so then you can come back and do the necessary changes. For example, if it is too large, you can reduce it. If it is too small, you can increase it. So these are the factors that are basically working on the load combination. So ultimate load combination that you do with the 1.4 and 1.6 times span. So altogether it will be coming 477. So the shear force is 235.5 kilonewton. So limited to the shear values 1.2. You remember probably that the square root of f dash c. So the v is equal this one. So the b, the nearest b is required to the 25 millimeter. So then the breadth we decided, so 275 millimeters. So this is the one way of doing the initial sizing. But in your case, we have given the sizes. And also don't misunderstand that. So the design, even for the same kind of load combination, there can be a different depth, there can be a different width also. All these different depth and the width, you need to design, you need to decide, and also you need to plan it out based on the architect's requirement. So this is what we need to do. And don't think once again that any kind of structures that you need to have a single size of element. There is no such. So unless or otherwise architect confirm it, it is adhered to the basic requirement of this structure, you may able to proceed that. Then you know the minimum requirement of the reinforcement, that is 0.24 and the 4%, and other one is a 0.13, that's a doubly reinforcement 4%. So all these two conditions are being applicable for the beams and also the any type of the flexural element. So whatever the times you decide, you can see here based on the steel strength 250, it's mean the mild steel, and the 460 is the tow steel. If it is a 250, you use instead of the 460, you need to go for the equation number 1. But today's situation is completely different. We don't do the main reinforcement designs under the mild steel category where the 250s come. So then the first equation can be easily forget it, and you can work only with the second equation. Keep in mind the minimum requirement is 0.13 and the maximum is 4%. So the spacing in between the bars, H aggregates and the plus 5 millimeter, or else the bar size in each and every time. So the SP is the maximum width. So it's a 300 millimeter and the 160 millimeter. So all these things also need to consider the minimum spacings of the reinforcement bar. The third one is a curtailment. The curtailments is a one way of making all the sections economical, and wherever necessary reinforcement only be provided. The in between, probably the sagging moment at the mid span and the hogging moment at the supports get the maximum steel, where down and the top. Then after that you can do the curtailment as you want. So it says the theoretically 50% of the bar may be the curtail from the A and B and shown below. It means you can go up to the 50% of the curtailment depending on the movement, flexural movements. So the flexural happens in the section. But anyway, these curtailments, one thing you need to be very careful that there may be in the different cases if the point loads comes. So the curtailment would not be possible in a different section, because sometimes the higher movements are coming closest to the support. Then once you are going to do it, it won't be an easy for site to manage it. So the curtailment, if you are doing the curtailment, you should practically see the two different things. One is if it is possible at the site. The other one is if it is really making a savings or the economical section. If these two are working, so then you still be able to work on. So these are the fully anchorage length, So the plane tension, the compression, and the deformation. So this is LA, it's a diameter type. So then you can multiply it by the diameter of it has written here, however, in order to develop any stresses in these bars, they must be anchored into the concrete. Except at the end support, the bars are therefore normally extended beyond the theoretically cutoff point. It means from the where the curtailment is taking place. The greater of the D or the 12.5, also where a bars is stopped in the tensions one full zone, anchorage length is stipulated below. So this table you can always keep with me. Actually, in a structural engineering, if you have this document in hand, so mostly whatever the tables you require and the clauses you required are fine here, and the procedures also you may able to find here very quickly. So this is what it says, the cutoff point 50% of the bar. So what you do is if you the total length in between based on the cantilever one, this is a cantilever one, the cutoff what you can do, right? So this is the simply supported or the continuous beam. This is one of the code, the graph. You can practice it, but anyway, here you need to make sure that the curtailment is taken on the right bending moment. Then anchorage and at the support, the east tensions bar will be deemed properly anchored if they extend. So the 12.5, it's 12 times the diameter. So say the CL type support, it means the end support, and the 12.5 times the face support. So if it is the face, it has to go another D over 2. So this is what it says. So all of you need to make sure that to ensure these anchorage supports at the columns where top of the columns where the beams get in off. This is actually we haven't much concentrate on our lectures, but anyway it says the bending rotations, also the curves and everything. I leave it to you. The curvature is R minimum minus 3.5 or the 4.5 if it is greater than the 25 millimeter. So the mildly steel, of course, the stirrups comes in the play. So it allows you to the quick, it means the sharp curvature because of their strain. this mild steel is where higher strain comparatively the high steel. So because of this, the energy absorb capacity of the mild steel is comparatively high. So then easily you could bend it. For the 90 bend, LA is equal whatever the 4RA less than the 12. For the hook, LA is equal 4RA divided lesser than the 24. To enable the continuity of the reinforcement at the construction joint and to enable bar lengths to be manhandled, laps bars are normally detailed. So it's less the minimum lap length is 15.5 or 300 millimeter. Tension laps, the use anchorage less L over LA. So where the phi is the diameter of the smaller bar. Always the phi is referred to the smallest diameter bar. The compression laps is used 1.5 times the compression anchorage length. So this pretty much clear for you guys, right? So this is all about the practically applicable for the guidelines and how you calculate the initial sizes and the thumb rules and whatever the codal provisions given to you. Okay, so then okay, I think this document also will be shared with you. This document contains all the type of the calculations which you need to get in your design example, right? Beams, slabs, columns with the joints, walls, corbels, cantilever structures, transverse structures, footings, pile caps, etc. But anyway, you need to take attention of the basic elements of the design. So I will leave most of the things that you can read and understand it. Let me quickly go to the one example. Start with these things. So up to now we have discussed all these anchorage and the length, the normal detailing practices, etc. Right? So in everything it comes here. This is kind of the loading arrangement, right? How do you analyze the structure, right? The combination of the structures. So in a maximum support reaction, so if you know here you will see the 6-span continuous beam. So the fully maximum support reactions conditions, you fully loaded it with the particular loading conditions, loading combinations of the ultimate. That is called 1.4 times GK plus 1.6 times the QK. So then what you can do is you can find it out at least few combinations to find out the envelopes of the bending moment diagrams. So the envelopes you can see here, this is 1.4 times GK, 1.6 times QK, and next one is a 1. It means only for the 1.0 times the dead load. So then that will be coming to the serviceability limit. So all these combination you put into the structure, at least 3 combination, and you try to find it out the envelopes of the frame analysis. So the moment distributions as plain here. The respective spans of the 5 meters are shown here, right? This is the work example number 1, all right? So this is the beam, etc. Then you can find it actually in your case, in our case, usually we find it out the beam section only. This is the flange T-type section where the effective beam width also being considered to the section. Support moment reactions, the curtailments, I said to you, how do you find it through the bending moment envelopes? This is the work example, the reduced moment through the moment example, right? Then the moment distributions are shown here, right? So easily you can read it and understand it. So let me actually quickly go for the a few example. These are we had discussed the nominal covered, the fire ratings, and the durability considering. So the stress block, how it is derived, how the final equations are coming, the derivation, the modifications factor, the reinforcement calculations, right? This is kind of the example where the bending moments comes, and how do the section is 500 by the 400, FCU is 35, the cover is equal to the 40 millimeter, moment is 246. So hereafter the D effective depth you can find it out, the epsilon you can find it out, M1, so the factor, so it is lesser than the 0.152. So some code it says specified the 0.156 in 1997, so don't worry about that. So then it is lesser than that, it is a single reinforcement, other than that it's a doubly reinforcement. So finally you will find the AC is required 1865. It is used 2T35 plus 1T25. So the M2 is similarly, you can repeat the equation, but here one thing is M2 over FC UBD square. So it is coming 0.179. So it is greater than 0.152. So that it is defined as a doubly reinforcement. D dash is this one. By equation 3.3, AC is equal BD, M over BD is squared FCU minus K. So then the minimum requirement has been satisfied. So that, in the reinforced beam, the minimum reinforcement is the 0.13% and the 4%. In between, you can put the whatever the reinforcement you calculated based on the equation you provided. So this is how the final calculation of the above example. All right. So I will leave you with the beam. So you can refer this document and get it done. Okay. This is slab design. You can see how it is being derived for the equation and so the design of the shear reinforcement, I don't think I should spend much time on this. This is slab design, right? The people ask what is the one-way slabs and the two-way slabs. So let us see these. You can see Lx over Ly, the span 4 meter, right? The sizing of the limited aspect ratio is 25%. So then you can calculate it. If the Ly over Lx is, this is two-way slab, 4 sides simply supported, right? So this is how it is calculated. So likewise, then you come to the column designs, column straps, etc. Then you can in your designs you calculate the what are the effective size of the columns, how you find it out, the areas of the stirrups, etc. This is design of the shear reinforcement once again. This is a kind of flat slab work example. So we don't have any designing of the beam here. Only the slab also all there's a two types of the slab. I mean, here we don't discuss in your module, but anyway, without beam you can also the foot in the slab. So that is one of calculation here. You can avoid it actually. So let us see the column design. Column designs, we know the first steps. Simply, let me summarize it. First thing is the find out the effective height, the conditions at the tops and the bottom condition. Then you find it the effective. Then the whether it is short or the slender. Then the brace and the unbrace. Then you know the it is axially loaded only or the axial load from the uniaxial. The axial load plus the biaxial movement. So these are the mode of the end condition. You hope you remember it. In the table, it's specified to find out the beta value. The beta value is required to find out the L effective. So this is how the end conditions are defined, right? So this is one example. The slender brace columns, grade 35 cross section is B800 and IX, IY is also 8 meters. So it means the both side beams depths are equal. So after that, you can find it out LEX over LH. So the major axis, the base on the minor axis, take K is 1, beta, you can find it out. So all these things is to be taken from the code of practice where the equations come, then you can calculate the required steel. This is the axially loaded the columns, so the beta value from the coefficients. These are the tables that you remember 100 days over BD. If there is the moment plus the axial loads comes together all the time, you need to make sure that the providing the required elements. So this is kind of the section that after designing. So it's huge load. This is also a design. This is also the critical regions reinforcement enhancement with the shear links. But anyway, you don't need to do that at all in your calculation. I will avoid these column beams joined that you can read and understand in it, but not much important at this stage. These are cobble designs in the future type of the bridge arrangement, and if the beams are launching in top of the beam cobble, this is how the way of doing it. So let's directly go for the footing designs. Okay, so this is the footing design. So the analysis and the designs of the footings based on the assumptions of the rigid footings, because we considered the column is the footing is bearing the axially loaded, or else if there is any movement, that movement can be also integrated to the footing design. So this is the two types of the footings we usually do with the isolated. So the first one is only axial load, the second one is axial for the moment. So both you can see how it is applicable to the design of the reinforcement. One thing is the critical shear and the punch in shear. So the work example is given here, you to understand, right? So then the total movements, I think we had discussed many times the work example also. So these are the type of the combined footings, right? So earlier we were talking about the isolated footing. So likewise, you can calculate the punch in shear on the work example and see whether the required reinforced the punch in shear is below the available one. Okay, these are the modeling of the software as the foundation modeling. So with this, I will be sharing with you this document as well. So then you can find it, go through it and do the necessary calculation for your design report.